Hi, class. So I'm going to go over what we did in class today briefly and add in a couple more examples. I'm getting a couple emails about that having some issues with just um, molar mass and moles, and I totally understand. It's been a long time since you guys have done chemistry, so let me just go through today's work, and hopefully this video will help you. So we'll start with the opener that we did today. So in the atmosphere, we have oxygen, and I need to, here we go. So oxygen is O2. So oxygen, if you look on the periodic table, oxygen has an atomic mass of 16. So 16 times 2 gives a molar mass of 32 grams per mole, which means that oxygen will weigh 32 grams if you take and then if you have 1 mole of it, you definitely have 32 grams. This is kind of the relationship between grams and moles. Now, for nitrogen, we have N2 because nitrogen is also diatomic. So we have 2 times 14, and so we have 28 grams per mole. And then finally, argon here is about 40 grams per mole. You may have seen it at 39.95 grams per mole. And argon is not diatomic. It is just Ar. Okay, so 7 diatomics. I'm going to switch my pen to a little thinner. And my handwriting's not the best, so please bear with me. So the 7 diatomic elements are H2, O2, N2, F2, Cl2, Br2, and I2. So this means as elements, just as elements, they exist as 2 atoms bonded together. So hydrogen molecules, so they look like this. All of these look like that. But if we make compounds with them, they don't necessarily have to be H2 or O2, right? This is only when they're elements that they're diatomic. Okay, so make sure you did that. And very helpful weekly schedule posted on Google Classroom. Okay, so here, the only ones that are elements are 1 and 2. Okay, they're composed of only a single type of atom. So these are elements. Elements are pure substances that are composed of only single types of atoms. Right there's your answer. So which boxes contain only elements? And there's a little explanation there. Which boxes contain pure substances? So pure substances can be elements or compounds. Okay, so if we take a look here, only 1, 2, we know those are elements. And if we look here, all of the particles in 3 are the same. So again, 3 is pure. But if we look at 4, there are different types of particles in 4. So the first 3 are pure substances, but the 4th is a mixture. So again, we're trying to go between these 3 levels of chemistry. Read that over. Okay, so when we were looking at the representations before, here you can write down a description of what this is. So here's a blob, that's just H. Now we have 2 blobs. This is 2 hydrogen atoms. So now we have 2 H. Over here we have 1 hydrogen molecule because now we have two H atoms connected together, bonded together. So this is H2. When we have subscripts after the element symbols, they're showing some kind of, first of all, that we have two hydrogens, but they are connected, they are bonded. Here we have three hydrogen molecules. Okay, so this would be 3H2. So the number in front gives the number of particles, 1, 2, 3. But this 2 indicates how many of those atoms are in one unit of that substance. Okay, so we have two hydrogen atoms bonded together to make a molecule. All right, so you guys got to do this on the Jamboard. So let me go over these again so you can look at them again. So 3 nitrogen molecules. So if we take our blue, we know that nitrogen is diatomic. Ooh, let me erase that and make a better nitrogen molecule. Okay, so we have 3 nitrogen molecules. This is 3N2. Okay, so now for H2O, we have 1. There's nothing in front, but that implies a 1. We have 1 water molecule. Okay, so I can take my oxygen, here's an oxygen, and I have 2 hydrogens bonded to it, and I use red for oxygen. So there's my 1 water molecule, and that's represented as 1 H2O. Mixture of water and nitrogen. So let me see, maybe I will make, I will make 3 water molecules. Okay, so I'll make 3 water molecules here. And I guess I will make 2 nitrogen molecules. So this is going to be 3 H2O plus 2 N2. Okay, over here we have red represents oxygen, black represents carbon. So this is 3 carbon dioxide molecules. And no worries if you don't know the name of that or even water, because you know what? We're just going to learn all this stuff this year. So 3 carbon dioxide molecules, symbolically that's 3CO2. Okay, 3Na. Na, we're going to use, I believe the color we're using is, maybe it's, well, I'll use purple. So Na, Na, Na. So that's 3 sodium atoms. Okay, 2 formula units. Now this formula unit thing is kind of a new term. This is what we use to represent lowest ratio of ions in an ionic compound. Okay, so now in sodium chloride, we don't have distinct molecules. We have a crystal lattice. So here's our Na. Chlorine, we're going to use green. Here's another green chlorine. And we have another sodium chloride, and they're all connected together with ionic bonds. Let's try to make that the same. And remember that they have charges, so our sodium, oh, sorry, go back here. That's not our sodium. This is our chloride. Chloride has a -1 charge, chloride has minus, and our sodium has a plus charge. So here we have a sort of a little lattice of sodium and chlorine atoms together. All right, so let's take a look at the next slide. Calculating molar mass. So just as a reminder, this 2 means that there are 2 aluminum atoms. This 3 outside the parentheses means take the stuff inside the parentheses and multiply it by 3. So here inside we have 1 chromium, but since there's just 3 out here, we have 3 chromiums. And over here, since oxygen is O4, right, we actually have 12 oxygen atoms, right? So we have 12 oxygens, we have 3 chromiums, and 2 aluminums. For the molar mass, we have to add up all of these atomic masses multiplied by the number of atoms there are. So first, we'll do the aluminum. So aluminum is going to be 2 times, and I'm going to try to use some more precise molar masses here. So I'll use 26 point, let's see here, 98. Okay, so 26.98, and these are grams per mole, plus the chromium. Okay, so the chromium is about 52 times, and there are 3 chromiums, okay, plus oxygen is 16 times 12. So if we take my calculator, multiply this and add it, plus 52 times 3 plus 16 times 12. I'm getting a total of 401.96. Let's use 2 decimal places. We'll make this 16.00 to make it more, make sure our sig figs are correct. So there's our molar mass of aluminum chromate. Is this an element, compound, or mixture? Well, it's a compound. We have more than one type of element bonded together. What's the name of it? We're going to spend a lot more practice time on this. This is aluminum chromate. Okay, now the particles in the single formula unit are going to be something like this. Okay, so we've got Al plus 3, got another Al plus 3, and then we have this polyatomic, which is actually covalently bonded. So the polyatomic is Cr with 4 oxygens around it, and there are 3 of these. So Cr, 1, 2, 3. And here's another one. And don't worry about the placement of these right now in the lattice. You're not expected to know the actual structures of these ionic compounds. Okay, those are oxygen, so that's why I'm coloring them red. Okay, so that is our formula unit of aluminum chromate right there. And this is used as a coating for metal plating, very tough coating. So what do we use molar mass for? We're going to go between moles and grams here. So here's our first example. We started with sodium, and I believe we had 50, no, we didn't have 50. We had 10 grams. And I'm going to add some decimal places here. 10 grams of sodium, and we want to go to atoms of sodium. So first, to get from atoms to, go from grams to atoms, we have to stop here. We need to get to moles. Okay, we have to go through moles to get to atoms. So what we're going to do is multiply, okay, by our molar mass, but we want to get rid of grams. So we're going to say 1 mole of Na is 22.99 grams. So that cancels that out. And then to change moles to molecules, or in this case, atoms, because we have sodium, multiply by Avogadro's number. Trying to be good with my sig figs here. Is 1 mole of Na. So that cancels that out. And so if we take 10 divided by 22.99 times 6.022 times 10 to the 23, we will get atoms of sodium. So I'll put that in my calculator here. So 10 divided by 22.99 times 6.022, I get over here 2.62 times 10 to the 23 atoms of sodium. That's probably about a teaspoon or tablespoon. I think about a teaspoon of sodium, maybe a tablespoon, but that's a lot of atoms. So our second example, we use sodium chloride, and we started with 0.5 moles of sodium chloride. And we wanted to get to chloride ions this time. Now over here, atoms and molecules, this is basically the particles that something is composed of. So this could also include ions if it's an ionic compound. And molecules, remember, ionic compounds don't have molecules, so these could be formula units as well. So here, if I want to go to ions, I'm first going to figure out how many formula units I have in 0.5 moles of NaCl. So here we have 6.02 times 10 to the 23rd formula units for 1 mole of NaCl. And then if I multiply here, I can see from my formula that I have 1 Cl ion, right, for every 1 formula unit. So I have 1 Cl ion for every 1 formula unit. So I can cancel that, and that will give me the number of Cl ions. So that's half of Avogadro's number. That would be 3.01 times 10 to the 23. Okay, and that's how. And okay, I'm back. Let's, I believe everything's working again. My AirPods died, and so time to go back to the old-fashioned way. Let's go back to the Unit 1 slides. All right, so we were here. We found the number of ions. Now, let me do one more example. I wasn't able to spend time in class doing this, but, I think probably another example might be helpful for people to see. So let's start with something like CO2. Okay, so let's start with the number of molecules this time. So what if we have 5.56 times 10 to the 22nd molecules of CO2. And let's say we just want to get some oxygen atoms out of this time. Well, we can look at the ratio of the atoms to the molecule in this formula. So I can see right here that for every one CO2 molecule, I see 2 oxygen atoms. So there are 2 oxygen atoms for every 1 CO2 molecule. Okay, and that cancels out, and we get our oxygen atom. So it's just 2 times 5.56. So if I take 2.5.56, I get 1.11 times 10 to the 23 oxygen atoms. So that's kind of how we'll convert between the distinct oxygen atoms and from the molecules. Now, just a reminder, what if we go from, if we only had moles instead, moles of CO2, and we wanted to go to oxygen atoms. Okay, so now what I'm going to do, I can use the same ratio that was in our molecule to convert my moles of CO2 to moles of oxygen. So I'm just going to say, oh, well, for every 1 mole of CO2, that's equivalent to 2 moles of oxygen, right? I can get 2 moles of oxygen out of every 1 mole of CO2. So if I multiply here and say, oh, 2 moles oxygen divided by 1 mole CO2, that cancels that out. And then I have moles of oxygen, but I want oxygen atoms. Well, I just need to multiply by Avogadro's number, 23 atoms over 1 mole of oxygen. And this is oxygen O, right? Because we're talking about atoms here in this case. So maybe I'll just take that out. But that cancels that out, and I will get from 5.56 moles of CO2, I've got to multiply that by 2, and then by 6.02 times 10 to the 23rd. So I'll punch that in. You can pause and do that yourself if you want to pause the video. And so I get 6.69 times 10 to the 24 oxygen atoms. Okay, so and always good practice to box or circle your answers when finished so that we can see where the answer is. All right, so here are these practice conversions. So I will post the answers to these, but I'm going to just do them out right now on here so that you have both the video and audio and the written version as well if you want to look along. So if I look here, okay, so I'm going to just grab those conversions on a different screen so that I can see them. Bear with me as I try to maneuver my screen around. All right, so here we go. On your sheet of paper, for number 1, molar mass of glucose, C6H12O6. Thanks for catching that typo there. earlier. So we have 6 carbons, so 6 times, I'll use 12.01 for now. We have 12 hydrogens, I'm going to use 1.01 plus 6 oxygens. So I'll add this all up. I think it's about 180 if I remember correctly. And technically I should put the 00 here to make sure my sig figs are correct. So this is 180.18 grams per mole for glucose. If you rounded these molar masses, that's fine too. Right now we're more concerned about whether you can do this. Okay, so now ammonium sulfide. So NH4 taken twice, S. So here, the 2 out here, right, there's a 2. So now we have 2 nitrogens. So 2 times 14.01. So there is our nitrogen here. Plus, we've got 8 hydrogens. 8 times 1.01. There's our hydrogen. And we have only 1 sulfur. So 32.06. We add that together, we should get the molar mass of ammonium sulfide. So 2 times 14.01 plus 8 times 1.01 plus 32.06, 68.16 grams per mole. Okay. I think my handwriting is maybe getting a little better. Okay, grams of glucose in 0.35 moles. 0.35 moles of glucose. And we want to get to grams. So I'm going to use my molar mass here that I calculated earlier. So 180.18 grams for 1 mole of glucose. Moles cancels out. And I multiply 0.35 times 180.18. And I will get 63.63 grams of glucose. Okay, so far so good, hopefully. 4, okay, is 0.35 moles of glucose again. And this time they want grams of carbon. Okay, so what am I going to do? So I know that in glucose, we have C6H12O6. So I want to figure out how many moles of carbon I can get out of this many moles of glucose. So I know from my formula, I get 6 moles of carbon for every 1 mole of glucose. And that's from my formula. So now I can go ahead and change this to grams of carbon. So that's our final goal, grams of carbon. So I multiply by 12.01 grams for 1 mole of carbon. That will give me my grams of carbon. And let me cancel my units, make sure I'm getting the right thing. Okay, 0.35 times 6 times 12.01 is going to give me 25 point, and we just need 2 sig figs, so 25 grams of carbon. And let's get rid of, ooh, wrong button, just get rid of this stuff right here if I can. That is my eraser, I think. Maybe I have somehow lost my annotation. Oh, there's my eraser back. Let's go back here. Back. Nope. Redo this. Okay, well, and then that. Okay, so we're on number 5 now. Okay, so we need moles of oxygen gas in 55 grams. So 55.5 grams. And oxygen gas would be O2, so be careful. Remember, oxygen is diatomic, so 1 mole O2 over 32 grams, okay, is going to give us the moles of oxygen gas. So I can just take 55.5 divided by 32, and I get 1.7 3 sig figs moles of O2. Okay, 6. So 60 grams of Al is how many moles? So 60.0 grams of Al is how many moles? So I want to, again, take this to moles. 1 mole Al divided by 26.98 grams. The grams cancel out. I can divide this out. 60 divided by 26.98. And I have 2.22 moles of aluminum. All right. Now, number 7. We have 60 grams of aluminum is how many atoms of aluminum? Well, we knew that this was from number 6. This is equal to 2.22 moles of aluminum. No need to do that part again. So I'm just going to take this and multiply it by Avogadro's number. And that will give us our atoms for 2.22 moles. And I'm getting 1.34 times 10 to the 24 atoms of aluminum. Okay, number 8, grams of Na and 4.5 moles of Na. And we want to get to grams. Again, here, multiply by the molar mass. Grams mole Na. Okay, so here can just multiply 4.5 and multiply by 22.99, and we get 103. And I will put that down as grams of Na. Okay, number 9, 0.567 moles of argon, okay, times, okay, we want to find atoms. Okay, so let's multiply this by Avogadro's number just to get our atoms. Atoms in 1 mole of argon, 0.567 times 6.02 times 10 to the 23, and I'm getting 3.41 times 10 to the 23 atoms of argon. Okay, so let's do the last 2. Number 10, what's the mass of 2.34 times 10 to the 24 molecules of C6H12O6? So we want to find the mass of this. To get to mass, we need to go through moles. So we know that 1 mole of glucose is 6.02, funky 2, times 23 molecules. That is a 2. Okay, and then we want to go from moles of C6H12O6, our molecules are gone, to grams, and we have that from before was 180 point, can't see it now, but 180.18 grams for 1 mole of C6H12O6. So that cancels out. And again, we're going to multiply 2.34 times 10 to the 24th, then divide by 6.02 times 10 to the 23rd to get the moles, and then multiply by 180.18 to get grams. Okay, so we got a total of 700 grams of C6H12O6. Okay, so those are our conversions. Make sure you become proficient with these conversions. We're going to be using mole mass particle conversions all year. And hopefully I did not make any mistakes doing this, but if I did, please let me know because I like to correct my mistakes. Oh, and we have not finished because I see that there's one last problem, which I almost skipped. So atoms of oxygen in 2.34 times 10 to the 24 molecules of glucose, which is C6H12O6. So what are we looking for? We're looking for atoms of O. So we want atoms of O here. So we know that in one molecule of glucose, we have 6 O atoms. Oh, I'm going to write that differently because that looks like a 60. We have 6 atoms of O for every 1 molecule of C6H12O6. So that will give us atoms of oxygen. So that cancels. So we multiply 2.34 times 10 to the 24 times 6. That should give us the atoms of oxygen. So I'm getting 1.40 times 10 to the 25 atoms of oxygen. And I don't know why I have another equal sign there. Oop. Get rid of that. So that's our atoms of oxygen. So these are our conversions. Review them. If you're having trouble, please come to office hours. Okay, so let's go on here. Okay, we finished all of these. And we were kind of at the very end, and I was like, oh God, trying to cram in more. And I probably should have just ignored that and just let you work on those conversions. But please, if you have time, take a look at this build an atom thing and just play with it and review how the protons, neutrons, and electrons relate to the atomic number and to the mass number and how the electrons affect the net charge. So as I mentioned, and I'm not sure anybody was listening because probably everybody was still working on the conversion problems, the number of protons in the nucleus are basically the atomic number. It's the ID number. So tomorrow we're going to be looking at these two atoms or ions. I'm not saying whether they're atoms or ions, as well as these, and trying to connect them to this word, isotopes. Okay, so trying to figure out if these are isotopes of a certain element. And if you want to review what that is, that'd be great. Okay, so that ends part 2 of today's material. And if you have questions, please email me, or just you can send me a message in Google Classroom as well about the assignment. And happy to get back to you. Also, office hours are going to be Tuesday from 2:15 to 3. And we will also have office hours on Thursday night from 7 to 8. Okay, hope you had a great day.